Now, my dears, the section A, first section in this chapter, we had discussed about all theoretical questions and answers, and in section B, we have finished all the numericals from illustrations, and now in section C, we will be going for exercise MCQs in the textbook. So, that is why I written here section C for MCQs. Okay. Kindly read the statement of first MCQ in the textbook exercise. MCQ number 1. Read it? Look. Coulombian force given by Coulomb's law is magnitude wise F equals to K Q1 Q2 upon R square. But this Coulombian force initially they have given as phi. Okay? Whichever symbol they give, we must adopt their symbol. Okay? Now, new Coulombian force I am taking F dash. I am taking F dash. And this small k is constant. But in the new or in the final condition, they have said in the statement that magnitude of both the charges is made doubled. So, double than Q1 I am writing 2 Q1, double than Q2 I am writing 2 Q2. But the distance between two given charges is made half. So, half of R, that is R by 2 and its a square. Now, simplify. 1 upon 2 square will be 1 upon 4. 1 upon 4. So, denominator will go in the numerator. 4 to the 8 to the 16 K Q1 Q2 upon R square. Q1 Q2 upon R square. Correct? Now, this 16 as it is. But what about K Q1 Q2 upon R square? In place of this part, you can write phi. So, in place of this part, when you write phi, now the final answer is 16 into phi. 16 into phi. Okay? This is the new Coulombian force. In the same question, suppose they ask, what is the percentage increase in the Coulombian force? What is the percentage increase in the Coulombian force? Or suppose they ask, what is the increase in Coulombian force in percentage? Correct? What do we mean by increase in Coulombian force? Greater minus smaller. Greater is the 16 into 5, that value, and minus smaller value was 5. So, 16 phi minus 5, that is 15 phi. But that 15 phi is the value, but you want that value in the percentage. You must multiply by 100 percentage. So, it is 1500 percentage of phi. That is 1500 percentage of initial Coulombian force. Okay, fine. Now, kindly read the statement for MCQ number 2. Read it? Come on. They are talking about placing an electric dipole in a uniform electric field. What is the resultant Coulombian force? Let us find out. You know, electric force is charge into electric field. Charge into electric field. For first charge, if you take positive, I should write here small q. But if second charge, if you are taking negative charge in the dipole, then you must write here minus q. Why here vector E and here also vector E? Because you are given uniform electric field whose strength or intensity remains same everywhere. Okay? So, write here also vector E, here also vector E. This is the electric force on a positive charge, this is the electric force on a negative charge. Correct? But now we are interested in finding out resultant Coulombian force exerted on entire dipole. That is, you must make vector addition of these two individual forces. That is vector F1 plus vector F2. It is this plus this. So, q vector E minus q vector E will be 0 vector. Correct? Please remember this result. For any electric dipole, when it is placed in uniform electric field, there is no resultant Coulombian force exerted on it. Okay? That resultant Coulombian force has come out to be 0. Okay? Read the statement of MCQ number 3. Read it? Look. We are given electric field of a point charge. Suppose that point charge is positive. For a positive point charge, you know its electric field is represented by such radially outward electric field lines. Radially outward. Okay? Now, along this direction, suppose I place an electric dipole in this manner such that its dipole moment from negative to positive charge is in the direction of this electric field. Okay, fine. Now tell me, compared to this positive charge, this negative charge is closer to this positive charge, correct? This is source charge. And when this is closer, naturally here stronger electric field is existing. When stronger electric field is existing, the electric force exerted on it would be stronger. And compared to this position is further away from this charge, and because this distance is more, here electric field is less. When electric field is less, then electric force also will be less. That's why I am showing here shorter arrow, and here I am showing longer arrow. Moreover, this positive charge will attract this negative charge, so this force vector is greater, and this positive charge will repel this positive charge. So this repulsive force I am showing this way, correct? But here this force is greater, this force is smaller. Show this force by longer arrow, this force by a shorter arrow, correct? Now tell me, both these force vectors are aligned along this line, okay? Means they are collinear. And when two forces are collinear, what about resultant force? You should always find out this way, bigger minus smaller, if they are in opposite direction, okay? Then resultant force is bigger minus smaller because this is in this direction and this is in this direction. Both of them are in opposite direction, and that's why we are taking bigger minus smaller. Come on now, consider an electric dipole whose dipole moment is in this direction from negative to positive charge, and which is aligned parallel to this electric field line, okay? This charge is closer to this positive charge, so this attractive force is greater, and this charge compared to this charge is farther from this charge, and because it is farther, this electric force is smaller. This positive charge will attract this negative charge, this positive charge will repel this positive charge, right? This attractive force is greater, this repulsive force is smaller. But if you see that directions, not only they are opposite, but they are aligned along same straight line, meaning thereby they are collinear. Whenever you have two forces and which are collinear and opposite in directions, you may find out resultant force bigger minus smaller, okay? But such forces which are collinear will have no perpendicular separation between their lines of action, correct? Because they are collinear. So when there is no perpendicular distance between the lines of action, they cannot produce any torque. They cannot produce any torque. Because the formula of torque is magnitude of either force multiplied by perpendicular distance between lines of action of two oppositely directed forces. But that perpendicular distance right now it is 0. So there cannot be any torque produced by such two forces, correct? So in this case, torque exerted on this dipole would be 0. That's what I have written here, tau equal to 0, correct? But it is one of the possibilities. One of the possibilities, if you place electric dipole this way, then only the resultant torque exerted on it would be 0, correct? But if you place it in such a manner such that vector P is not in the direction of electric field or not even opposite to that, and if you place it randomly in other situation, there will be certain torque exerted on the dipole. So among given options, one of the option is that resultant torque on the dipole may be 0 in the electric field of a point charge. That option is true, correct? Fine. Now kindly read the statement of MCQ number 4. Read it? Come on. My dears, we are given two particles. One is electron, another is proton. Both of them are placed in uniform electric field. Let us find out magnitudes of electric forces exerted on them. Magnitude of electric force exerted on electron. Let us find out first. Electric force exerted on electron. What do you mean by electric force? Charge into electric field. Charge into electric field. But charge of electron is minus E. Correct? Now take magnitude on both the sides, then you will get Fe equals to plus E into E. Correct? Now in the same uniform electric field, now we place proton. The electric force exerted on proton is charge into electric field. Correct? And now take magnitude, you will get Fe equals to E into E. Correct? You can see these two magnitudes are equal. No doubt magnitudes are equal. Fe equals to Fp. But so far directions are concerned, this force is negative, this force is positive, meaning thereby they are in opposite directions. Okay? So among given options, in one of the options they have given that in this case magnitudes of electric forces exerted on electron and proton would be equal. That option is correct. Magnitudes would be equal. Correct? Fine. Now before we go further, I would like to tell you something extra which will really help you in solving further numericals, further MCQs. Look here. What is that extra fact you must come to know? Coulombian force, general formula for Coulombian force for any medium, you can write this way: 1 upon 4 pi epsilon Q1 Q2 upon R square, where epsilon is permittivity of given medium. If it is vacuum, you may write here epsilon 0. If it is not vacuum, any other medium, then its permittivity epsilon you must write over here. Okay? But don't you know dielectric constant of a given medium is defined by ratio of permittivity of a given medium to the permittivity of vacuum. Remembered? Find out epsilon from here, transfer this. Epsilon will be epsilon 0 into capital K. Epsilon is replaced by epsilon 0 into capital K. Correct? Rest of the terms as it is. Fine. And now just give it equation number 1. From this equation number 1, we will obtain 3 very good relationships which will be further utilized in the further MCQs. Okay? First of all, you find out F into K. F into K. So just transfer this K over here. That's all. F into K. It will be Q1 Q2 upon 4 pi epsilon 0 R square. Q1 Q2 upon 4 pi epsilon 0 R square. And now tell me, when you are talking about two given charges separated by given distance, then Q1, Q2 R, they are constants. And when these three are constants, epsilon 0 is as such constant only. So this whole right hand side will be constant. Correct? So when F into K is constant, mathematically you can write F1 K1 equals to F2 K2. F1 K1 equals to F2 K2. Okay, fine. Then secondly, you just find out K into R square from here. So find out K into R square. Just make it subject of the equation. Transfer this F in the denominator. So K into R square will be Q1 Q2 upon 4 pi epsilon 0 F. Q1 Q2 upon 4 pi epsilon 0 F. Correct? And when you are talking about two given charges and given amount of Coulombian forces exerted between them, at that time Q1, Q2 and F, they are constants. Epsilon 0 is as such constant only. So this right hand side will be constant at that time. And when this part is constant, mathematically you can say K1 R1 square will be equal to K2 R2 square. K1 R1 square will be K2 R2 square. Correct? Fine. Then finally, you just find out R square into F. R square into F from this equation, you will get R square into F will be equal to Q1 Q2 upon 4 pi epsilon 0 K. Q1 Q2 upon 4 pi epsilon 0 K. When you are talking about two given charges placed in a given medium, at that time Q1, Q2 and capital K, they are constants. So this whole right hand side will be constant. In short, R square into F will be constant. And when R square into F is constant, mathematically R1 square F1 will be equal to R2 square F2. R1 square F1 will be equal to R2 square F2. Okay? And if you want to remember all these three results very easily, that too without any mistake, I am just suggesting you to remember one cyclic triangle this way. This is that cyclic triangle. Look here. Suppose that I am writing here F, Here I am writing capital K, that is dielectric constant, and here I am writing R square. And just go clockwise, suppose, then you may remember this way, F into K, K into R square into F will remain constant. F into K, K into R square into F. Come on, F into K, K into R square into F. Last time, F into K, K into R square into F. F into K, K into R square into F. Correct? But once again I am reminding you, when you will write F into K equals to constant, when you are talking about given charges separated by given distance. When you will use this relation, K into R square equals to constant, when you are talking about given charges and given Coulombian force exerted between them. And when you will use this relation, R square into F equals to constant, when you are talking about given charges placed in a given medium. Okay, fine. Now kindly read the MCQ number 5. Read it? Come on. They are talking about given charges separated by given distance. When given charges are separated by given distance, you can use this relation, F into K equals to constant. F into K equals to constant. Correct? So mathematically F1 K1 is equal to F2 K2. F1 K1 is equal to F2 K2. What is F1? First value of Coulombian force which they are given as alpha. What is K1? Dielectric constant of first medium which they are given vacuum, and for vacuum dielectric constant is 1. How? When you are finding dielectric constant for vacuum, you should write here permittivity of vacuum which is epsilon 0. Epsilon 0 upon epsilon 0 will be 1. So this is dielectric constant of vacuum which is 1, and this is new Coulombian force which we are looking for, and this is the dielectric constant of another medium which they have given as capital K. Now find out F2, transfer this. So it is alpha upon K, correct? So new Coulombian force will be 1 upon K times or kth part of initial Coulombian force. I repeat, new Coulombian force will be 1 upon K times or kth part of initial Coulombian force. Got it? Fine. Now kindly read this statement of MCQ number 6. Read it? Come on. We are given 2 point charges. One is 4q, another is minus q. Let this be first charge, let this be second charge. Now, along the line segment joining them, we are placing third charge exactly at the midpoint, such that this charge which is minus small q should remain under equilibrium. That is, the resultant Coulombian force exerted on this charge should be 0. For that sake, what should be the third charge, capital Q? Its polarity we have to find out and its magnitude also. Let us find out both. If you want to find out polarity and magnitude from the same step, same mathematical step, I am just suggesting you one very easy way. You just do one thing. You want resultant Coulombian force exerted on second charge to be 0. Then you simply do one thing. The scalar addition of, or you can say addition of magnitudes of Coulombian forces exerted on this charge should be taken 0. Take summation of magnitudes of Coulombian forces exerted on this charge to be 0. On this charge, which other charges would exert Coulombian forces? Rest of the charges that are, come on, first and third. Come on. On second charge, whatever is the Coulombian force exerted by first charge, I am showing by symbol F21. On second charge, whatever is the Coulombian force exerted by third charge, I am showing by symbol F23. And as I said, summation of magnitudes of Coulombian forces exerted on second charge should be taken 0. Last time, On whichever charge you want resultant Coulombian force to be 0, please do one thing, you take summation of magnitudes of Coulombian forces exerted on that charge to be 0. Okay. What is F21 by Coulomb's law? K Q2 into Q1 upon R21 square. What is R21? Distance between second and first charge. Similarly, what about F23? Come on, K Q2 Q3 upon R23 square, and that should be taken 0. Correct? Now tell me, K Q2, this much part you can take common. Inside the bracket, Q1 upon R21 square, Q1 upon R21 square plus Q3 upon R23 square, Q3 upon R23 square, that should be 0. Transfer this K into Q2 in the denominator on the right hand side, 0 upon anything will be 0. So now this part is 0, this part is 0. And now this Q1 is the first charge, magnitude of first charge, which is 4 into small q upon R21 square. R21 means distance between second and first charge. Distance between second and first charge, they have given this total distance as small r. So small r square. Plus, what about third charge? Magnitude of third charge I am taking capital Q. This is the third charge, which is capital Q. Okay. And divided by R23 square. That is square of the distance between second and third charge. Distance between second and third charge. Distance between second and third charge is this much distance, but because this is the midpoint, this distance will be half of this, that is r by 2, and it's a square, and that should be 0. Now just simplify this term as it is, but r square upon 4, denominator will become numerator. So 4 into capital Q upon r square, that should be 0. Transfer this part on the right hand side, from plus it will become minus. Now cancel whatever you can, 4 ones are 4, r square ones are r square. So Q equals to minus Q, Q equals to minus Q. So you can see not only we are getting magnitude of this charge, but we are getting polarity of that charge, it must be negative. If it is negative, then only this charge can remain under equilibrium. Why? Because this is certainly positive and this is negative. So this positive will attract this negative charge this way. So direction of F21 is this way, towards left hand side. And now if this is negative, then only this negative charge will repel this negative charge. And so the repulsive force will be this way, opposite to this. And now these two forces are oppositely directed, and if they have equal magnitudes, and then the resultant Coulombian force on this will be 0, because these two forces are collinear. Collinear means along same straight line, but they are opposite in direction. And now if they have equal magnitude, then resultant Coulombian force exerted on this charge will be 0, and then only this charge will remain under equilibrium. Correct? For the last time I am repeating that fact. On whichever charge you want resultant Coulombian force to be 0, on that charge, remember the summation of magnitudes of Coulombian forces exerted by rest of the charges should be taken 0. Correct? Then you will get in the answer the polarity also and in the magnitude also. Okay? You will get both polarity as well as magnitude. Now read this statement of MCQ number 7. Read it? Come on. We are given one circle of radius small a, over which there is non-uniform linear distribution of electric charge, and it is given by this formula, lambda equals to lambda 0 cos theta, where lambda is linear charge density which varies with theta as per this formula. Okay. Now what about linear charge density? It is charge upon length, dq upon dl. This is the charge of charge element, this is the length of length element. This right hand side as it is. Come on, dq as it is. When you select extremely small length element over this circle, then it will give you very small length of circular arc. And what about very small length of circular arc by formula? I told you to remember radius into extremely small angle. radius is A, extremely small angle formed by that extremely small circular arc at the center is d theta, and this lambda 0 cos theta as it is, correct. Suppose they give here alpha cos theta instead of theta, suppose they give alpha, then you may write here A into d alpha. Right now it is theta, so variable should be taken in terms of theta, so I am writing d theta. Got it? Fine. Now transfer this. So it is A lambda 0 into cos theta into d theta. A lambda 0 cos theta d theta. But this is the charge present over considered extremely small length element, correct? But we want total charge, come on, total charge located on that circle, and just to find out that total charge, what you should do, you should go for taking summation of this partial amount of electric charge. Summation you can find out mathematically by taking integration. So integration dq. But when you take integration on left hand side, you must take integration on right hand side also. Come on, A lambda 0 is constant. Integration of remaining part, that is integration cos theta d theta. But mind well, you should take integration in such a manner that all the charge elements which are arranged continuously over the circle must be accommodated, and for that sake you must go for closed integration, correct? Closed line integration, fine. And here when you want to go for closed line integration over the circle, then in 1 ton you can just vary this angle theta from minimum to maximum. Minimum value of theta is theta equal to 0, and maximum value of theta is theta equal to 2 pi radian in one revolution, correct? For 1 circular ton, the minimum value of theta is 0, maximum value of theta is 2 pi radian. Got it? Fine. Now, summation of partial amounts of electric charge will give you total charge on that circle. Let it be capital Q, which we require to find out. A lambda 0 as it is. But what about derivative of sin theta? It is cos theta. Now speak reverse, integration of cos theta will be sin theta. Integration of cos theta is sin theta. But the limits are from 0 to 2 pi, 0 to 2 pi. This A lambda 0 as it is, instead of theta, we should write 2 pi first, and after putting minus sign, we should write the lower limit, that is sin 0, correct? Sin 2 pi is also 0, sin 0 is also 0, 0 minus 0, 0, 0 into this will be 0. Total charge on that circle is 0. Now you may wonder that we have some linear charge distribution over a given circle, and when we are finding total charge comes out to be 0. How it is possible? Yes, it is very much possible, because in this formula there is a cosine function, okay? Mathematically we have found that total amount of charge is 0, but how would you understand this from physics point of view? I am showing you. Suppose that circle is like this, having its center at the origin. Say this is positive x-axis, negative x-axis, positive y-axis, negative y-axis, okay? In short, here it is origin. And now you can think of this quadrant as first quadrant, this is a second, third and fourth. First, second, third and fourth. Now tell me, don't you see here in the formula there is a cosine function, and you know from mathematics, in the first and fourth quadrant this cosine function is positive. If this is positive, lambda 0 is already positive. Positive to positive will give you positive. When value of lambda is positive, it indicates the presence of positive charges. That's why on this part of the circle which lies in first and fourth quadrant, I am showing the presence of positive point charges, correct? And now tell me, in the second and third quadrant cosine function is negative. Minus into plus will be minus, so lambda will be minus. When value of linear charge density lambda is negative, it indicates the presence of negative point charges. That's why on this part of the circle which lies in second and third quadrant, I am showing the presence of negative point charges, correct? And so far the quantity of charge is concerned, let me tell you, whatever is this positive charge, same is this negative charge. So naturally when you make the algebraic summation of these two equal amounts of electric charges with opposite polarity, it should come out to be 0. That's why this total charge is 0. Got it? Fine. Now read the MCQ number 8. Read it? Look. Initial Coulombian force between two identically charged identical spheres A and B is, suppose F, it is K QA into QB upon R square. They both have equal amounts of charge, each of them is small q. So this is also small q, this is also small q. So small q into small q, that is small q square, and the distance between them is r. Okay, F equals to K q square upon r square. This is the initial Coulombian force between charged identical spheres A and B when they are separated by distance r. Just give it equation number 1. Now what is done? The sphere A having charge small q is now brought in contact with another identical sphere C which is initially charged less, and then they are separated. Fine. If you bring identical spheres in contact and when you make them separated, remember equal charge present on both the spheres now is summation divided by 2. Summation divided by 2 because you are bringing contact of two spheres, that's why summation divided by 2. If you are bringing three spheres, three identical spheres in contact, and then if you are separating them, then you can say equal charge on all the spheres would be summation divided by 3. Okay. Right now we are bringing only two spheres in contact and then we are separating them, then the equal charge present on both the spheres would be summation divided by 2. Come on. Charge on sphere A is q and charge on sphere C initially is 0 divided by 2. Summation divided by 2. So what is this now? Q by 2. This much equal amount of electric charge will be present on sphere A and on sphere C when you make them separated. Okay. So in the final condition, so I am putting QA dash, QC dash. Dash indicates final condition. Okay. And now what is done? Now the charge on sphere C is Q by 2 and that sphere C is brought in contact with a sphere B which has charge Q, and then after they are separated, when identical spheres are brought together, brought in contact and then they are separated, if you are bringing two identical spheres in contact and then if you are separating them, then equal charge present on both of them will be summation divided by 2. Come on. What is the charge on sphere C? It is now Q by 2. What is the charge on sphere B? It is Q, summation divided by 2. Now this is 3Q by 2 upon 2, that is 3Q by 4. But this will be the charge now on sphere C in the latest condition, and that same amount of charge will be there in the final condition of sphere B. Correct? Now, what is the charge finally on sphere A? It is Q by 2. What is the final charge on sphere B? It is 3Q by 4. And now they are brought at the same distance r. Then what is the Coulombian force? Let it be F dash. New Coulombian force I am taking F dash. Come on, small k as it is, constant only. Instead of QA, new charge on sphere A I am taking QA dash. Instead of QB, new charge on sphere B I am taking QB dash. And new distance between them, instead of r I am just putting r dash. Okay. Put up the respective values. K as it is. What about QA dash? QA dash is Q by 2. Correct? Into QB dash. What is QB dash? Right now it is 3Q by 4. 3Q by 4. And this is the final distance between spheres A and B, which they have said in the statement it is to be kept same as earlier distance. Earlier also it was r. Now also this r dash is r only. So now I am writing r square. Simplify. 3 upon 4 to the 8. 3 upon 8 I am just separating into k into q, that is q square upon r square. But now tell me, wherever it is kq square upon r square, you may write capital F. So in place of this part, I am writing capital F. So it is 3f upon 8. 3f upon 8. Got it? Fine. Kindly read the statement of MCQ number 9. Read it? Look. We have 2 point charges, one is small q, another is 4 into small q, then separation between them is given to us 30 centimeter. Fine. We are asked along the line segment joining their positions, at which point should we get resultant electric field to be 0. That point, that position we have to find out. Let us find out. Such a point, such a position where resultant electric field becomes 0 is called a null point. Is called a null point. Now, first of all, try to understand that how that resultant electric field becomes 0 at that point. How I am showing you. Suppose that position is this. Okay. Now tell me, for a positive point charge, don't you know the electric field produced by positive point charge is always away from it. So away from this positive point charge. So it should be this way. It should be this way. Fine. And what about direction of electric field produced by this positive charge? It should be away from this. So it should be this way. If you take this charge as first charge, then direction of electric field produced by first charge is this way towards the right hand side. I am writing E1, and direction of electric field produced by this second positive charge would be away from it, will be this way. That is E2. Okay. Now you can see that directions are along the same straight line, meaning thereby they are collinear. And now if their magnitudes are equal, then resultant electric field at this point will be 0. Correct. And such a point which I told you, null point, remember it is always closer to bigger charge. Sorry, closer to smaller charge, away from bigger charge. Closer to smaller charge, away from bigger charge. Closer to smaller charge, away from bigger charge. Closer to the smaller charge, I have taken this distance as x, and away from bigger charge, this distance will be total distance minus this distance. Total distance they are given 30 centimeter minus x. So I am writing 30 minus x. Okay. Now tell me, in order to have resultant electric field at point P to be 0, oppositely directed electric fields must have equal magnitudes. That is, E1 must be equal to E2. What is formula of magnitude of electric field produced by single point charge? Come on, KQ upon R square, K into charge upon distance square. K into charge upon distance square. Here it is E1, so I am writing K Q1 upon R1 square. Here it is E2, come on, K Q2 upon R2 square. K will cancel. So left is Q1 upon R1 square should be equal to Q2 upon R2 square. What is Q1? Q1 is Q, correct? R1 square. What is R1? Distance of point P from first charge, which is x. So R1 is x, its a square. What about Q2? Magnitude of this charge is, come on, 4Q, correct? Divided by square of distance of point P from second charge. Distance of point P from second charge is 30 minus x, and so it's a square. Now simplify. Q1s are Q getting cancelled. Left is 1 upon x square, take square root, it will be 1 upon x. Here 4 upon 30 minus x whole square, take square root of 4 is 2, square root of this is 30 minus x. Now take cross multiplication, 30 minus x will be, come on, 2x. Transfer this will become plus 2x plus x, that is 3x, find out x, 30 upon 3, that is 10 centimeter. But mind well, this is the distance of point P from smaller charge, that is small q. That is also correct answer, but it is not there in the options. In the options, they have given distance of point P from this bigger charge 4q. You can see from the figure, distance of point P from this bigger charge is this much, which is 30 minus x. So what we require is to find out 30 minus x, okay? Come on, 30 as it is, x value we have found out 10 centimeter, 30 minus 10, that is 20 centimeter, correct? Whether you say 10 centimeter from small q, or you may say 20 centimeter from 4q, it is one and same. But in the option, they have given this as an answer. Got it? Fine. Why you got this position somewhere between these two charges? Because both of them are like charges. For a system of two like point charges, remember the null point is always between them. Okay? Always. Because then only you will have one direction towards right hand side, one direction towards left hand side, then only you will have opposite directions, and if the magnitudes are equal, then resultant electric field at that point will be 0, correct? if this charge is positive and this charge is negative, then in that case you will not get the null point between these two. No, you will get on either side, either this way or this way. Okay. Kindly read the statement of MCQ number 10. Read it? Look. Come on, Coulomb's law for two charges placed in vacuum separated by distance r. Magnitude is F equals to 1 upon 4 pi epsilon 0 Q1 Q2 upon r square. Transfer this epsilon 0 here, transfer this F in the denominator. So epsilon 0 will be Q1 Q2 upon 4 pi r square F. Now we are asked to find out permittivity of this vacuum, dimensional formula of permittivity of vacuum. Come on, whether it is permittivity of vacuum or permittivity of any other medium, dimensional formula will be same. Let us find out dimensional formula for this, and for that sake you just put that symbol in this such a bracket and then write down dimensional formula for each of the quantity on right hand side. For these two charges, they have given in the statement that take dimensional formula for charge as capital Q. So this is charge, I should take capital Q. Here also this is charge, I should take capital Q divided by square of r, that is square of some length. Dimensional formula is L raised to 2, and this is force. For force, what is the dimensional formula? M raised to 1, L raised to 1, T raised to minus 2. Same thing I have written here, just it's a matter of simplification now. Take this M raised to 1 up in the numerator, will become M raised to minus 1. L raised to 1 plus 2, that is 3, take it up, L raised to minus 3. This T raised to minus 2 going up will become T raised to plus 2. Q into Q, that is Q raised to 2, you may write. Okay. But this is as per the statement given in the textbook. Sometimes they may ask the dimensional formula of permittivity in terms of capital A, capital T. At that time, you should write in place of Q. Remember, the dimensional formula for electric charge is A raised to 1, T raised to 1, A raised to 1, T raised to 1. And when you make it squared, it will be A raised to 2, T raised to 2. And T raised to 2 will be multiplied with this T raised to 2, altogether T raised to 4. So in that case, it will be M raised to minus 1, L raised to minus 3, T raised to 4, A raised to 2. Correct? Fine. Kindly read the statement of MCQ number 11. Read it? Come on. Magnitude of electric dipole moment vector, small p equals to, by formula, 2a into q. Remember the definition? Product of magnitude of either charge in a given electric dipole and the distance between two unlike charges in that dipole is called electric dipole moment of that electric dipole, shown by symbol small p. What about value? Value of small p, they are given 3.4 into 10 raised to minus 30 Coulomb into meter, capital C small m, Coulomb into meter. And what about 2a? It is distance between two unlike charges, which they are given 1 angstrom. Here you are taking this electric dipole moment in Coulomb into meter, then this distance you must convert into meter. Angstrom to meter multiplied by 10 raised to minus 10. And this is the magnitude of charge, okay, which we are looking for. Simplify, answer is Q equals to 3.4 into 10 raised to minus 20, that many Coulomb. Because this rest of the values we have placed in SI unit system. SI unit of electric charge is Coulomb, symbol is capital C, don't put any full stop, okay. Come on my dears, kindly read the statement of MCQ number 12. Come on, read it, look. We have one square lying in the XY plane, that is in the plane passing through X and Y axis. Right now you may consider like a surface of blackboard, okay, fine. we have electric field directed along z axis. Tell me, if this is positive x axis, this is positive y axis, where is positive z axis? This way, perpendicularly outside the plane of the figure, perpendicularly outside the plane of the figure. Okay, fine. So you may think it this way, if this is positive x axis, this is positive y axis, then this is positive z axis. Okay, perpendicularly outside the plane of the figure. Okay, now along same direction we have electric field. Now we are asked to find out total electric flux linked with this square in the presence of this electric field. Very simple. Whenever electric field is existing, and in that electric field which is uniform, if you place some square, some plane surface perpendicular to it, then all the electric field lines will pass through that surface perpendicularly. So it will have some electric flux which we require to find out. For any plane surface which is kept in uniform electric field, how would you find out electric flux? By a formula, phi equals to AE cos theta. Correct? What is A? Given area for a square, it is square of side length, that is L square, into E as it is cos theta. What is theta? Angle between area vector and electric field. Tell me, if this is the planar surface, then area vector is to be drawn always perpendicular to that plane. So if that planar surface is like this, then perpendicular to that, then you may draw area vector like this. Correct? Perpendicularly outside. Correct? When this area vector is also perpendicularly outside the plane of the figure, electric field is also perpendicularly outside the plane of the figure, and these two vectors are pointing in the same direction. That's why angle between them is 0 degree. Correct? Now simplify. This side length for a square you are given 10 centimeter, centimeter to meter divided by 100. 10 upon 100, that is 0.1, and it's a square. What about electric field? They have given in the statement 100 Newton upon Coulomb. Now this multiplication is 1. What is the SI unit of electric flux? Newton into meter square upon Coulomb. Newton into meter square upon Coulomb. By chance if you forget, then just recall the unit of electric field which was Newton upon Coulomb. What about unit of area? SI unit meter square. Got it? Fine. Can you read the statement of MCQ number 13? Read it? Come on. We have uniformly charged spherical shell, and we place one point charge, say 10 microcoulomb, at the center of that spherical shell. We are asked to find out electric force exerted on this point charge. Don't you know formula of electric force? Charge into electric field. Now tell me, where have you placed this point charge? Inside the spherical shell. But in the theoretical part of this chapter, we had studied for any charged spherical shell, there is no electric field inside the shell. So because this charge is existing in the inside region where there is no electric field, right now is 0, and when for the inside region when electric field is 0, 0 into E will be 0. Correct? So no electric force will be exerted on this point charge because of absence of electric field. Got it? Read now MCQ number 14. Read it? Come on. Electric flux linked with any closed surface according to Gauss law, it is sigma q upon epsilon 0. What do you mean by sigma q? Algebraic summation of charges enclosed by given closed surface. And right now they have given two charges which are enclosed by the given closed surface. One is plus 10 microcoulomb, another is minus 10 microcoulomb. naturally their addition would be 0, 0 upon epsilon 0 will be 0. This is what we get mathematically phi equal to 0. But try to understand why total electric flux linked with entire closed surface, why it is 0, I am showing you. If you consider a positive charge inside the closed surface and equal magnitude of negative charge inside the same closed surface, then what will happen, I am showing you. For a positive charge, its electric field is away from it, correct. So, at that time electric flux due to that positive charge will come out of the closed surface, which should be taken positive. For a negative charge, its electric field is pointing towards it. So, at that time there is some incoming electric flux, which should be taken negative, because incoming and outgoing electric flux values are equal, but one is positive, one is negative. Naturally, the total, that is resultant electric flux linked with entire closed surface will be 0, correct. Fine. For any closed surface, remember now onwards, incoming flux is to be taken negative, whereas outgoing flux is to be taken positive.